Many thanks, Helena, for the nice introduction. And while we wait for the slides, yeah, it's great to be here. First time in Toulouse. Yeah, here's the presentation. For those of you who don't know where Trento is, maybe you're following the Olympic Games. There are some races like cross country, I think, in the Trentino area, not in Trento, of course, but in the region. It's pretty large, so sitting between the Dolomites and the mountains, so it's quite nice between Italy and Austria. What I'm going to talk about today is about some applications of, let's say, scientific machine learning, how it's called today, in the field of cardiology, of course, computational cardiology. So let me start to say something about the heart. So we all know that the heart is a pump, a mechanical pump, so it pumps the blood throughout the body. Maybe it's a bit less known that it is an electromechanical pump, so there is an electric signal that orchestrates the contraction. And of course, when you have an arrhythmia, hopefully not, you may have also mechanical and so functional problem, so to the hemodynamics part. It's quite well studied, the heart, also from a numerical point of view, as you may know, because it's genuinely multi-scale, multi-physics, so you have electrophysiology, as we are going to see today, mechanics, CFD, so fluid dynamics. There is also some feedback due to physiology, feedback loops, and so on. It's quite complex organ. Also, the anatomy is complicated in terms of geometries, large deformations, of course. There are valves that are also moving a lot. It's quite challenging, and that's why maybe numerical analysts and scientific computing people, they like working in this context. If you like Lego, there is also a version there, the Lego version. There was also a torso, but this was not space for that. Okay, but the anatomy is not that relevant except for the fact that it is a complex architecture, so to say. There are several challenges when you do cardiac modeling. Some I already mentioned. So it's a multi-physics problem, as I said. It has complex solutions, so similar to what we have seen before. That's an example of atrial fibrillation simulation. You can see these nonlinear waves, so traveling waves that are going throughout the domain. These are self-sustained solution. The typical PD is a reaction diffusion system. So these are solutions of a parabolic equation, not hyperbolic, although you have these traveling waves. It's a time-dependent problem, as you can see there. The one problem that I will focus on today is that we have complex domains, so complex geometries, not just in the shape of the domain itself, but also in the parameters. So there are highly heterogeneous parameters. In this case, the black regions are what we call fibrotic regions, that they typically appear by aging. Okay, it's an aging process, and this can be the substrate for arrhythmia. So complex parameters as well. Another difficulty is that it's patient-specific. So if you train a surrogate model for your heart, well, you have to select which is the patient that you are training your surrogate model for. Okay, if you do several simulations of one geometry, then you move to another patient, it's a different geometry. So you cannot reuse your surrogate model because it's geometry dependent. That's a big problem, of course. And we work with clinicians, and clinicians, they like speed. Okay, so there is a need for speed. So if you collaborate with them, typically you get a question on Friday and they expect an answer on Monday. But that's, of course, that's not how it works in science and research. But certainly there is a need for speeding up these simulations to hopefully to real time. So a lot of challenges. I will be focusing mostly on complex domains today, but I will show you also some. I will also touch some of the other topics. So since the session is about scientific machine learning, I will focus here a bit on physics-informed neural network that we didn't discuss today, actually, that much. So I will give you a very brief overview of what's the idea. So the idea is actually very simple. There are two components, say. One component is that you want to approximate all your fields by neural networks. Okay, so if you have a solution, an unknown, we have seen before, with CFD solutions, with the MLP approximation, here you can have the same. Okay, so you give an X, you can get your output, what can be of any form. In this case, it's a scalar quantity. That's the first ingredient. The second ingredient is that you don't solve the PD exactly, you don't enforce it exactly, but you do a sort of a least square approximation. Okay, so it's a sort of a regression problem. So essentially what you do is you have a loss function. Oops, I didn't, oh, yeah, but that's good to keep. You have a loss function, and then what you try to do is to minimize some mismatch to data points, the PD, so this is typically the residual of your PD, and then some boundary condition, okay, that you want to minimize. In general, it's not going to be zero, it's going to be small. So if you know least square Galerkin method, it's in a way similar without the data term. Okay, this has been popularized by this paper by Raisi and others. Of course, we have seen an explosion of applications in this context. We did also some. You can see here some application. I will focus maybe on the first one later. We have a collaborator in Chile, and we've been working a lot on using PIN or PIN-like ideas to cardiac application. But I will not go in the details into this, but all of these are driven by PIN application in a way. So you can see that it's not, let's say, simple solutions in a way. Now, one issue that we faced was how to work on complex geometries. So the key idea here is that, in general, neural networks are mesh-free. So I can get any point in space, R3 or whatever, R2, I evaluate and I get an output out of it. Whether there is a mesh, a geometry, well, it's just that you select the points on that geometry, but in principle, you can evaluate the neural network everywhere. Okay, this is an advantage. Of course, it's a strong advantage, but also a disadvantage. If you take, for instance, this example of an airflow, okay, this is not cardiac, but I think it delivers pretty well the idea. Your domain here has these pins here, and now your domain is highly non-convex with respect to R3, but your neural network, in principle, you can evaluate everywhere. So you can evaluate between, let's say, the voids or inside the pins. So the problem here is that what you get is that points that are geometrically closed, they may be topologically not closed. If you get 2 points here, I keep doing the mistake. On this pillar and this other pillar, of course, the distance is short, geometrically speaking, but the 2 pins, they don't talk to each other in some sense because they topologically are not very close. In principle, you can capture by the neural network, so you can fit a neural network by these, but you need to capture this frequency. Okay, so the frequency, I mean the distance, so your neural network must capture this distance in order to be able to accurately reproduce the solution. And that's a problem because neural networks, they struggle in learning high frequencies. We actually have touched this in the previous talk now with the Fourier features. That's essentially the idea behind that. I will talk about this later. But first, let me highlight this interesting paper that I found a couple of years ago, which is about doing regression intrinsic or extrinsically. So what's the difference? So in principle, suppose that you have like a dragon here or this kind of ring, double ring. So you have a field and you want to interpolate this field on this complex geometry. So what you can do is to try to do the regression problem, so to interpolate intrinsically on the curve or on the surface, okay? So you don't leave the surface or the curve, or you do extrinsically. So you embed your surface or curve in a higher dimension, the natural embedding space, R2 or R3, and then you do the interpolation in that space, okay? You see that there is a difference. Here it's pretty clear. On the dragon is a bit less apparent. Maybe you can see on the mouth here that the interpolation of this point here is that the mouth is not affected by this, but here it is, because of course the distance is not that high. And the question is how quickly you can converge when you do this, when you compare these two approaches. In general, you converge, so if you increase the number of data points, you converge, so that the shape of the geometry doesn't matter that much, but it matters in terms of a constant, if you want to see. so for instance, if you do on a sphere, which is a nice shape, okay, it's curved, but it's a nice shape, you don't see the big difference between doing extrinsic versus intrinsic. But if you do on the dragon, that you have these non-convex scenarios, then you see that there is a big difference. There is a gain in doing intrinsic regression with respect to extrinsic one. So in a way, be aware of the geometry that you are on the dragon and not you are in R3 matters. Okay, in terms of not in terms of convergence rate, but in terms of the constants that you can get. So when you are in a low data regime, if you want. Okay, so how to generalize then the PIN idea to complex domains? So we have to account for this intrinsic geometry, and the trivial idea that we actually took from Gaussian process regression. So if you want to do Gaussian process regression on surfaces, for instance, or manifold, you have to go through this process. In Gaussian processes, this is much better encoded in a way. But the idea is the following. So what you do, you encode the geometry via the eigenfunctions of the Laplace-Beltrami operator, which is used in shape analysis quite often. Essentially, you have to solve this PD here. This is a Laplacian. Well, this is an eigenvalue problem. So, of course, you have several eigenvectors and eigenvalues that they will, in a way, define your shape. Okay, not uniquely, but they define, in a way, your shape. To have an idea of how these functions look like, they typically oscillate. Okay, so the first mode is something like this, and then you see more and more oscillations. If you do on a square, on a cube, you get sines and cosines, so you get the Fourier series, essentially. So this is a natural generalization of it. So the idea then is the following. Instead of using, like we do, like Fourier features. So with the Fourier features, essentially what you do is to replace x and y and z as an input, you replace with linear combinations of sinus and cosine, so to say. Not linear combination, but say sinus and cosine evaluated with, let's say, some random coefficient. So what we did here is to use the eigenfunctions. So take, for instance, the cow here. You see that if you evaluate the neural network at the, let's say, the toe of the cow, you can have much more, let's say, variability if you use the eigenfunction. So you say you have more colors if you want here. So the neural networks is maybe able to capture the fact that you are on this region of the cow and not, let's say, an arbitrary one. In a way, you're trying to encode some properties of the geometry into the neural network, okay? But you do in a way that is independent from the neural network itself. So you compute the eigenfunctions, and then you use these as a positional encoding for representing the solution, okay? So it's a separate process. You're not learning these. That's an example. So I'll give you some example. Here we solve the econal equation. The econal equation is just, if you want to compute the geodesic distance, you typically solve the econal equation. No, this is the exact solution. So you see that's a spiral. That's the spiral is this here is or the coil actually is on purpose, no, because it is exactly the problem that I was discussing before. If you want to get from this ring to this ring, you have to make a turn, okay? So topologically, you're pretty far, but geometrically, you are close. Indeed, if you look at what PIN is doing, is not doing very well. This is what graph convolutional networks are doing. So they are aware of the topology, but they are much more noisy. And this is delta PIN and works pretty well. That's another example with the heat equation here. It works pretty well. Here we compare it also with another approach that is called sign distance function PIN. Essentially, you clip your solution by a sign distance function, just like a mask, and it works pretty well. We also did some numerical comparison. Graph convolutional networks are, I say, the main competitor in this respect, because you work directly on a mesh. And has been used quite extensively, but we show that in our case we can achieve a much better error compared to convolutional networks. What we suspect is that graph convolutional networks, they are still in a way local. The way they propagate the information is it's kind of a multi-grid way. You know, you go from local to global through some hierarchy, while for the Laplace-Beltrami operator, you have eigenfunctions that are globally supported, and so the information can travel much faster. Of course, when you solve a PDE, you want to find some global solution, or you're inverting a local operator into something that is global. Other example, we tried hyperelasticity here with an extra parameter, so it's like pulling this bar here and horseshoe shape, or we tried also a regression on the dragon. Okay, this is a standard mesh. It's not that we like dragons or something. It's there's a database of shapes, and you can find these, the bunny, and many others. So dragon is quite nice. We also tried other example like approximating the geodesic distance on a bunny, indeed, but I will not show this animation here. I want to show you another application instead of PIN, which we call the FiberNet. So it's actually an interesting problem that we encountered a few years ago, and that's the following. So the heart is made of, I didn't talk much about the heart actually until now, so this is the first part of it. So for the fibers, so the heart is made of fibers, and fibers are important for the electrical and mechanical function, okay? So the myocytes, they contract in the fiber direction, okay? So you see that the structure is not that trivial. There is this spiraling of fibers. These are real, let's say, histology studies. It's the ventricle, this is the atria, so you can see that are quite, there is some regularity, some structure. And the problem is how to get this structure without killing the patient, in a way, and extracting the heart. So you want to measure it. There are a few approaches to do it. One is diffusion tensor MRI. So essentially, you can correlate the diffusion of what you get from diffusion tensor MRI, particularly the eigenvectors, with the fiber direction. Typically, you take the first eigenvector of each tensor in each voxel, and then these you associate with the fiber direction. That's an example. Now, diffusion tensor MRI takes a lot of time. Okay, typically you don't do on patients. There is no clinical indication for doing it, and if you did MRI at some point of your life, you know that it's quite. You have to stay still for a very long time, just to see maybe that you have some problem on the shoulder. So if you have to get the fiber direction here, don't forget that the heart is moving, usually, unless the patient is dead. And of course, that's another problem. So when you want to take snapshots of your fiber direction. Another approach is what we call in the field rule-based approach. So essentially, we use prior knowledge, and you build a set of rules, which are typically solution of PDs, to define a fiber field like this one. Okay, these are not patient-specific, but in a way are anatomy tailored. So you have anatomy, and you can build a fiber field on top of this. So what we decided to do is the following. We said, well, in clinics, what you typically do is to get these electroanatomical maps. If you go into ablation sessions, so they have to burn some part of your heart because you have an arrhythmia, they also take this type of electroanatomical maps. So this is the right atrium of a patient. You see that they go there with a catheter, and they measure the electric potential, and they move around, and they get a cloud of points with many potentials. So our idea is the following. Can we formulate these as an inverse problem? So we know that the fiber direction has an influence on the electrical activation because the signal is faster in the fiber direction. So we have a measure of the output. Can we invert the process and get the fibers out of it? So we did this with two approaches, with a PD-constrained approach, very classical, and then we also try with PIN. Why not? It sounds like an interesting application of it. Now, the formula is actually very simple. That's an example of a propagation of a wave. I don't know why it's clipped, but it should be. And you have the corresponding activation map. So the activation map is just the arrival time. Okay, you have a wave passing, and then you measure the time at a given point. If you have the activation map, which is like isochrones, like this, if you want to know the velocity, what you do is just to take the gradient of this map. The gradient gives you the propagation direction. The norm of the gradient is going to be the slowness, so 1 over the gradient is the velocity, okay? What we call the conduction velocity. So you have this very trivial formula that the conduction velocity is 1 over the norm of the gradient. Now, if you suppose that both are unknowns, you multiply, and you get this equation. No? Just multiply here, and this is the Econol equation. Now, what you can do is the following. You can say, Well, but I don't know the velocity. I have a partial information on the activation, a partial information on, well, I have no information on the velocity, but I know that the velocity will depend on the propagation direction because there are fibers, so along the fiber is faster. And it may depend also on other high-order parameters like curvature and so on. So the idea is to enforce the Econol equation as a constraint, well, a weak constraint, and then try to learn something about the velocity. For instance, here you have to decide how to formulate the velocity. The standard approach would be some Riemannian velocity like this, so the propagation is ellipsoidal. And this tensor D, which is local, encodes for the fiber direction. In particular, what we did is to use this log Euclidean metric that is a way to linearize the space of symmetry positive definite tensors. So we don't optimize for the fibers directly. We optimize for the conductivity tensor, and then we extract the fiber afterwards by taking the largest eigenvector locally. So this is the formulation. We have the loss function. You have some data. We have the model here. We also have some regularization for the conduction velocity. This is a total variation like, so it's a Uber regularization for the conduction velocity. And then there is the regularization for the weights of the neural network. You train, these are collocation points, and then you get, well, the animation that I showed before, actually. So here are some results. Of course, you can use multiple maps. So if you have multiple activation maps, and this can be simulated in the clinics, because when you do ablation, the clinicians can pace your heart at certain locations, so you get different activation pattern. And we see that more black the arrows are, the lower the error. You see that the fiber that we can reconstruct with respect to the ground truth is actually quite accurate. We also extended this to UQ, and so we combined these with the delta pin approach that I explained in the first part. And in particular, we extended to, well, include the geometry, but also to add the UQ part, so the assertive quantification part that we do with a simple ensemble method. So essentially, you train. We have seen also this in the previous presentation. It's a very basic approach. That's very important because then you can have statistics a posteriori. One thing that we notice here is that we didn't take the mean, okay? Because taking the mean, this is a nonlinear problem. So if you take the mean as an input, the output is not going to be the mean in general. So we prefer to use this medoid approach and then the disparity instead of the standard deviation, which is a better way to get, let's say, a consistent representative from a statistical point of view. Yeah, I mean, here you can see a comparison with the vanilla, say, FiberNet approach and the one with delta pin. We noticed that with the delta pin approach, we are much better in getting some, let's say, local spots. Here we added some, in this test, some spots that are low velocity, and these we can get much better with this approach. Okay, so we compare it. In terms of computational cost, it's actually comparable to PD constrained optimization. So we were surprised by that in a way, and it's quite fast. It's the order of minutes. I don't know how much time I have. Probably not much, I guess. Okay. I just wanted to say something about, let's say, more recent project we are working on, which is cardiac digital twin. So the idea is to bring the digital twin approach into the cardiac application. Here, of course, there are already some components in place. The idea is the following, that you have some data from the patient, so for instance, the electrical measures, imaging, and then you want to build a digital replica of the patient in order to inform clinicians and do therapy or, let's say, risk stratification and so on. Of course, there are a lot of components here to do. I will show you something very quickly on what we call the electrical twinning, so to go from the ECG to the electrical activation. In this case, if you look at the standard approach, you can take very dense recording, and this dense recording by the solution of an inverse problem, you can get the cardiac potential. There are technologies out there, so there are companies doing these, but the problem is that what if you want to do from the 12-lead ECG, the one that you do when you go to do a medical visit because you want to run a marathon or something? At least we have to do it in Italy to do that. So of course it's not high density like this one. It's very sparse. So here the key idea is to try to embed some modeling aspect into that. So the idea is that to do something more like this, that you model the cardiac activation by neural network or whatever, it doesn't matter. Then you have a propagation model, so we know the physics, so we know how to go from the heart to the surface ECG, and then what we minimize is some parameters within the model, or simply the mismatch by enforcing the model as a physical constraint. Okay, to these approaches that you can take. We recently published this paper where there are actually a lot of technical difficulties here in there. Essentially what we do, this is a physics constrained approach, so the physics is enforced point-wise. We have a complex propagation model that is then, you can see that the solution is not that simple. This is fed into a model to compute the ECG. And then what we do is to compute, essentially we are able to compute the derivative, if you want, of the mismatch with respect to the original parameter in order to have this optimization loop. This problem is highly non-convex. There are a number of parameters that we optimize are around 400, 1000. But with these gradient-based approaches, works pretty well. You can see this is the real animation. Typically, we do one iteration every 10 seconds, and we converge in a few hundred iterations. And then as an output, we get the fitted ECG, so we can reproduce the ECG, and we get a final activation map. You see that the solution is quite complex. We also have been working on the anatomy, on digital twinning, so what is called anatomical twinning. In this context, what we have done, well, here the state of the art is something like this. So you get this CT or MRI, high-resolution imaging. Then you mesh. You can imagine that this process is not that easy. You want to distinguish different organs, different cavities. You want to have a high-quality mesh, typically very fine. You can see here the mesh size. So these are meshes with several million of elements, actually 20, 50 million elements. So pretty large. But this is a problem in the sense that this high-resolution imaging is not very often available. So for instance, what if you start from echo? Echo is something you can do very cheaply. You just put a probe somewhere and you measure, and you see something like this. You see it's a very gross, let's say, very partial view of the heart. Oh, this is one view, this is a different cut. So our idea was to use a deep shape model to do that. It's a sort of a statistical shape model, but the idea here is again to use a neural network to represent the geometry, and then you can condition these with some latent code that in a way is surrogating the geometry itself. So that's quite interesting because then once you have this atlas, what you can do is also to try to build a new optimization problem. For instance, I know that if I change the latent code every time I sample a latent code, I get a different anatomy. So what you can do is to say, okay, let's try to see which anatomy is the closest to the data I have, and you can try to optimize these small networks. So the inference problem becomes a small optimization problem, and it's quite interesting because it works usually quite nicely. Yeah, this is essentially what I described. I think I will stop here because probably I have. Yeah, let's go directly to the conclusion. So there is still a lot of stuff that we want to do in this context: anatomical, electromechanical twinning. So adding the mechanics. I didn't discuss these. Some of the topics we have touched. No, so whether we should do physics constrained, so a full classic PD constrained optimization, or a physics informed approach, or a purely data-driven. I just run simulations and then I try to learn afterwards. So there is going to be a project starting in June in Trento, so lasting for 5 years. So there will be several open positions, PhD and postdoc. And we also have another project which already started, but the application will close in April, I think, which is on atrial fibrillation, and this is a training network. It's typically quite attractive for young students because these are European level projects. I don't think there is France here, no? Maybe next time we should think about it. But there are other destinations in Europe, and it's highly interdisciplinary. So if you're interested, just ask a question. I stop here. Thanks.
Okay, so many thanks to Simone. Do we have one very, very quick question? Okay, Paul.
Very, very quick answer then.
So thank you very much for your presentation. Just a question about the physical informed loss. So you added a PDE term but at the definition of pins, but it comes at a cost because it involves to back propagate through a back propagation graph. So it's difficult to say. But the pipeline, the whole pipeline of your delta variants would have worked, as far as I understand, without this term in the loss. Like if you had kept only the MSE loss, I think that it would have worked. So have you tried to compare your model with and without the PDE loss, the PDE residual?
Yeah, it's a great question. So I think it's more a philosophical question in the sense that when you do physics informed, in general, you don't need the forward problem to be well posed. For instance, you may not assign boundary conditions. For the econal equation, we have to assign where you start for the propagation, okay, the input points. When you do a physics informed, we don't do that. We discover that afterwards. So in a way, you are constraining you're putting a constraint between let's say, the velocity and the activation, okay? But you don't need to have the forward problem to be solvable, okay? Because you don't have boundary conditions, so it's not well posed. While if you do PD constraint optimization, the forward problem must be well posed. So you must be able to uniquely map input and output in order to make it into the. So of course, in the comparison, we take into account about that. So we know that there is a big advantage, if you want, because sometimes you don't know the boundary conditions, but this can be a problem because maybe it will affect the quality. So in terms of accuracy, we have noticed that is actually quite good, even though it's you don't provide the full data. By the way, of course, data will come from the data fidelity term. Okay. So you don't know the initial conditions, but in some way you are backtracking and reconstructing those from data. Okay, that's why you are able to solve the problem, although the forward problem is not well posed. Yeah.
Okay, many thanks to Simone again. And together with Olivier and Jérôme, we would like to thank you for coming to this session and invite you to poster session, I guess?
Yes.
Okay.
So, yes, so I would like to thank you for this last session, the organizers, so Alena, Olivier, Jérôme, and also to give a pointer to FISIM AI that was mentioned. So it's an interactive program run also by Paul, who is in the room. So if you want to join to work on this type of activities, please contact any of those people. So short notice, someone has lost his passport and phone. It's Arnaud Tivent. So in case Arnaud is here, he will be pleased to get that. Okay, nice. And now just for our schedule. So now we have a poster session. At 12:30, we have a lunch break. And at 2 p.m., we start the session with young fellows, postdoc, and PhDs. And this will be followed by the last session on robotics. So please, thank you very much again, and see you.